In the previous video, we looked at the forward pass of the reverse mode of autodiff or automatic differentiation. Now we're going to go through the reverse pass, and this is where a lot of the magic happens with regard to actually computing the two partial derivatives dz dx and dz dy. Now the way this is going to work is that each of these boxes corresponds to sort of one mini function, if you will, or one piece of the composition of functions. So g is a function of f, which is a function of both c and d. C is a function of a, which is a function of x. And we could do the same thing for this lower path. Now we do need to be careful when we do the reverse pass, because notice that x influences z in two ways, one via the top route and one via the bottom route. So we do need to realize that using the chain rule, we do need to have two terms for computing dz dx. But let's begin by just listing out the partial derivatives. So here, first of all, we actually do have a derivative here, and it may seem pretty trivial. That's going to be dz dg. Now remember, z is equal to g in this case. It doesn't always have to be, and that's why we distinguish them, because g could actually be an input into another piece of a second function or a different function. In this case, we only have one function, a scalar output for a vector input. So dz dg, because they are the same, it's going to be 1, right? It's kind of like saying, what's the derivative of x with respect to x? Right, and that is this. We know that that's 1, but ddx of x is the same thing as dx dx, right? That's just a different notation. And so a derivative of a variable with respect to itself is equal to 1. So I'm going to put that off to the end here. Then here I have g as a function of f. Now g is the output that we get when we take the natural log of whatever f is. So we're going to have dg df. And dg df, if you think about that, well, g is equal to the natural log of f. And what's the derivative of the natural log of f? Well, it's 1 over f. Okay, 1 over f. Now, what is f equal to? Well, f is equal to 22, so this equals 1 over 22. And as an approximation, 1 over 22 is about 0.05. So I'll just go ahead and round it. We know we could get some pretty good machine precision out of this. It's probably not enough, but it's good enough for illustrating what we're about to do. Okay, we keep working back because we know that according to the chain rule, all of these derivatives will multiply to get us back and to get us the dz dx and the dz dy. Now here we're actually going to have two derivatives, one for the bottom path and one for the top path. We note here that we actually have the function. Maybe I'll actually write the functions in. Here we had g equals the natural log of f. Here we're going to have f is equal to c plus d. And if we now take the derivative, and I'll put the derivative of df dd down here at the bottom, and I'll do df dc here at the top. Well, if you notice, f equals c plus d is just a linear function in c and d. So if we take the derivative of c plus d with respect to c, we get 1 plus 0, which is just 1. And df dd will be the same thing. The derivative of c with respect to d is 0, and the derivative of d with respect to d is 1. Okay, now we can take whichever route we want. Normally, this reverse pass is going to keep track of both derivatives, but up here we'll have, notice c equals 4 times a. And down here we have d equals 3 times. So up here we're going to have, we have c is a function of a, so we'll have dc dA. And, well, the derivative of 4a with respect to a is 4. It's like taking the derivative of 4x. The derivative of d with respect to b is going to just equal 3. And then we'll also have this derivative here and this derivative here. Here, notice that we have a is equal to x squared. And down here we have b is equal to x times y. Okay, so each of these steps, notice, requires a really simple derivative. It only focuses on one specific type of function like logarithm or a basic arithmetic operation, squares, things like that. So without much fuss, let's go ahead and tackle this one up here. Now I'm going to have two derivatives here. One of these is going to be the derivative of b with respect to y, and I'll put that down here. And holding x constant, the derivative of a constant times y is just the constant. And then up here, I'm going to list the derivative of b with respect to x because, again, we have another input coming in there. So we're going to have two partial derivatives here. And that guy is going to be y. Okay, and then up here, we have the derivative of a with respect to x. And the derivative of x squared with respect to x is just 2x. Now, here's the thing. We actually don't want 2x as an expression. We just want the value of what 2 times x is. We did that back over here where our derivative was a function of a variable. All of these other ones just turned out to be constants because of the types of functions we were dealing with. But here, we actually want to calculate, well, what is 2 times x? Well, if x is 2, then 2 times 2 is 4. And we already know that y is equal to 1 and x is equal to 2. So those are the values that, in other words, are getting multiplied together. Okay, so now we're ready to actually compute. Now, again, keep in mind how straightforward this was. It required just some basic computations. So now to get dz dy, and by the way, a lot of this is happening at the same time. We're just kind of doing this by first listing out the partials and then showing how we're going to evaluate them. But this automatic autodiff process could actually multiply things going reverse in the chain. So you can kind of look at this however you want. You can either look at it from the front towards the back or the back to the front. Let's go ahead and look at it from the back to the front. So from here we would have dz dg, and I'm doing dz dy first just because it only involves one following one branch. So basically we're going to multiply all of these lower derivatives here. We'll have dz dg times dg df times df dd times dd db times db dy. And now if our notation and everything is correct, we should get everything to cancel out. Notice that the b's cancel out here, the d's cancel out, the f's cancel out, the g's cancel out, and we precisely get dz dy. So all we have to do now is just multiply these together. So we'll have 2 times 3 db dd db times the derivative of f with respect to d, which is 1, times the derivative of g with respect to f, which is about 0.05, times 1. And so we get 6 times 0.05, which is equal to 0.3. All right, so that is the derivative of z with respect to y for the given values of x and y. Now we'll do the same thing for the x dz dx, but notice that we're going to have two derivatives. We're going to have one that follows up the top and then one that follows down the bottom, but then leads back up to the top over here. So I'll start with just the top route. And by the way, these are going to be the same up until we get to here. So we'll have dz dg. So now I'm just following backwards, times dg df times df dd. And oh, I'm sorry, that's going to be the lower route. So let's just take the lower route first. And then notice that when we go the upper route, it's going to be the same thing for the first two terms, and then times dg df, but then we're going to multiply by df dc, because now we're working our way upward here. All right, so the downward route, we have df dd times db e db. And here for that same derivative, we'll have dc dA. And then we move back 1. So for the bottom route, we'll have dB dx now, right? Because we want to work our way back up here, dB dx. And again, we want to just make sure that we end up with dz dx, which we do, because all of these guys cancel, and we're left with dz dx. Now using the top route, dc dA multiplied by dA dx, that will also give us dz dx, but from the different contribution of x just in that top term. And so again, all we have to do is multiply these together. So we have, these are both 1. df is about 0.05. df dd is 1 and df dc is 1. Then we have dd dB, which is 3, and dc dA, which is 4, and then dB dx, which is 1, dA dx, which is 4. And so we need to sum these together. So here we get 16 times 0.05, which comes out to 0.8. We get 0.8 plus, and then here we just have 0.15. So we should end up getting 0.95. And so there is our partial derivative with respect to y. Is this value, 0.3, and then z dx is equal to 0.95. So that is the reverse pass of this, and notice that occasionally we would need an expression like 1 over f, or over here where we had our derivatives which were a function of x, but notice they were really simple to take. Then that's the application of the chain rules, that each piece of the chain involves a simple derivative, and then we can use a series of intermediate steps to actually build up the derivatives that we're interested in. So this is automatic differentiation, specifically the forward and reverse passes of the reverse mode. Again, this is the one that we're focusing on here.